All right, welcome back. So in this video, we're going to tear through the code in Phase 7 specifically for the ball and actually get this thing bouncing around the scene so we have something to interact, or at least start interacting with our paddle and the bricks, so that then we can follow on with some scoring code and some points and that kind of stuff to transition between the different levels. So if we take a look back over here in Unity, you'll notice that off the ball, we had our script attached. So we need to open that up in Visual Studio. So we can double-click the ball script, and it pops up right here in Visual Studio, rather, not Unity. And so in order for the ball to work correctly, we need to start talking to that rigid body. Over here in Unity, if we take a look back at the ball, we have the rigid body here. And so we need to interact with it with physics. So back here in Visual Studio, if we drop down a couple of lines, right here at the very top of the class, we want to create a field section, just as we've done in the past. And the first variable we want is going to provide us access directly to the rigid body. So since the type over in the inspector was rigid body, we can start typing out rigid body, and you see that the tooltip here auto-completes and says, yeah, you're probably wanting to talk to a rigid body, and that is indeed the case. I'm going to, since that's the type, the next piece is the identifier, the name that I'm going to use throughout the rest of my code. And so here, I'm going to just summarize it to be RB, or abbreviate it to be RB for rigid body. Now, here in just a minute, we're going to hook that variable up, but as we continue working through this field section up here at the top, I can conceptually think about several of the other aspects that this ball is going to have as part of its gameplay just in general. The next piece is I want to be able to control the ball's speed as it bounces around the scene. Make it slower, make it faster, potentially increase difficulty to make the ball go faster, go slower, that kind of stuff. So in order to keep this information here in this file, but also keep it secret so nobody else out there, no other script can potentially mess with it, I want to be able to, at the very least, see it in the inspector so that I can customize it. As a designer, I want to be able to customize the value. And so I need to employ a serialize field. So we do our square brackets, followed by serialize field inside the square brackets. And immediately after that is the variable that the serialized field attribute will apply to. And that's going to be a float called speed. And I'm going to default it to a value of 10.0f in our semicolon. The next variable that I'm going to hold on to is actually going to be the direction. Now the idea here is as the ball is first starting out, right, when we complete the paddle code, the ball is going to be attached directly to the paddle. And as I line up my shot and I press the space bar, the ball is going to randomly pick a direction and then it's going to fire. So we're going to calculate a direction. Then as the ball bounces around, as it hits the walls, it hits the paddle, it hits the various bricks, it's going to reflect off of those surfaces. And as a result of the reflection, we're going to recalculate the direction as well. So I need to hold on to the direction itself. When I go to calculate it, I'll need a container, a variable, to hold on to that value. So here I'm going to have a vector3 called dir, short for direction. And we'll get into that code in just a second. Now, the thing is, as the ball bounces around the scene, there's a very real possibility that it's going to strike the edge of some of our bricks, the paddle. And so what ends up happening is there's this edge case bug where when the ball strikes at a very specific angle, we end up basically setting the velocity in either the x-axis or the y-axis to 0. And when we get into that situation, we basically lose the ability to continue playing the game. It's effectively frozen in that axis. So what we want to do is every so often, like as the ball is bouncing around the scene, we're going to periodically check its current velocity x and its velocity y, and if either of those two, or both potentially, of those values drop to 0, or more specifically, because these are floats, a value that's so close to 0, it might as well be 0, right? We deal with floating point error, which is a number so close to 0, we just say, it's 0, right? So in this case, what we want to do is say, if our velocity in the x or in the y drops below this particular threshold, we want to come through and just kind of nudge the value a little bit, right? Nudge the velocity in either the x or the y or both so that it gets the ball back into play, right? It allows it to, at the very least, start to bounce around the scene a little bit more, and then once it strikes the surface, it generally kind of recovers itself. Now, in order to do that, I need a value that's going to I need a single value. This one value is going to represent both the threshold that I'm looking for as well as the correction value that I'm going to apply to the velocity. And that's going to be a float, and it will be called nudge factor. And it's going to be a relatively small number, so 0.1 f. And then your semicolon. And so if we detect we're way too close to 0, we can kind of give the ball a slight nudge to get it back into play. Now, as the ball goes bouncing around the scene, we're going to listen to Unity, and Unity is going to tell us when we actually collide with a surface. Now, there's a slight problem there, because when Unity responds to a collision, it actually tells us about that event just like a frame or so after the actual collision happens. So what we need to do is, the information at that moment is going to be stale. It's going to be incorrect. It's like post-processing. So we need to get the pre-processing information. And that actually happens when another form of update happens. So update down here is happening every single tick of the engine whenever it gets a chance to during that frame. It might be called earlier, it might be called later, and that's where you'll see in some example code where people use time.delta time as a multiplier to kind of smooth out those numbers. Well, the thing is, the physics engine, the thing that responds to when we impact surfaces, that's actually calculating at a very specific frequency. That would be that 1 divided by 75 value we talked about earlier over in the Game Manager's Awake. We set it to run at a very specific frequency. And so when that system, the physics engine, is calculating its impact, that information is good. We want to preserve that information before we lose that information when we start responding to the collision. So in order to do that, I need a variable that can act as kind of a storage before the collision response is called. So that's going to be a vector3, and I'm going to name it velocity last frame. Okay, so with these fields, we can start setting up exactly what this program is going to do. Now down here inside start, this is where we're going to start making use of some of these variables. Now the rest of them will be used in update or a slightly modified version of update, and then some other methods as we continue on. Now, here inside start, the very first thing I want to do is, if I'm going to be controlling physics, I need to talk to the rigid body. And in order to talk to the rigid body, just like we dealt with the main text from the Week 2 project, where we captured a specific game object named main text and we asked for the component, here, we're going to ask for the component. The thing is, instead of looking for a game object named main text and then extracting a text object from it, here, the rigid body is actually attached to us, to the ball. So instead of looking for somebody, we are the somebody. So we can ask ourselves directly for that object. And if you recall from a few lectures back when I talked about how we inherit certain functionality from our parent, from our grandparents, and so on and so forth up the inheritance hierarchy, we have somewhere up through all the way up to about the let's see, if we click on this guy and press F12, and then behavior F12, and then component F12, right here at component we have game object. So we have the game object that represents ourselves over in the inspector. So if I come back over to ball.cs, inside start, basically instead of calling out to myself because I'm already here, I also have direct access to get component. So what I want to do is call out get component, call to the method get component, try to find a rigid body, and then hold on to it once I've captured that variable. Or more specifically, once I've captured that component, I want to hold on to it in a variable. So that RB that we worked with earlier, we want to set it equal to something. What are we going to set it equal to? Well, that's the component returned when we get component. And you'll notice there were a couple of versions in that listing there. There's 1, there's 2 right here. This version doesn't take anything right after it other than the parentheses. The next version has these less than, greater than symbols on here, and that is a system inside C# referred to as generics. Basically, it kind of customizes the method to be able to say what specifically we're looking for. So instead of looking for a whole bunch of things, we can kind of narrow the focus, narrow the search to look for very specific things. So in this case, it's also worth noting that if you have kind of a hierarchy over in your inspector where maybe the object you're looking for is on a child game object or it's on a parent game object above you, you can also take advantage of a few extra methods here. There's get component in children, looks through the child, your children below you, each child independently. And then there's a get component in parent, which will look for a specific component on your parent hierarchy. There are also plural forms of each of those methods. Get components. And right here, per the tooltip, it returns an array of that particular item you're looking for. So that's what the plural version does for every one of these. So here off of get component, I'm going to throw in a less than, and Visual Studio is going to give me the greater than automatically. And usually we will often refer to this as a diamond. So get components, or actually, no, sorry, correction. This is get component, not the plural version. I just want one. And inside the diamond, the less than, greater than, I want to specify what exactly I'm looking for. Well, what is RB? RB up here is a rigid body. So that's the type that we're looking for. So here inside the diamond, we're going to say rigid body. And then since it's a method, after the greater than, we need our parentheses and our semicolon. Now the idea here is if you accidentally stick with that plural version, it's going to return an array, and since RB is just a single object, you'll actually get an error. It'll say, hey, you're trying to return an array into a single object. I don't know what that is. So you'd have to either change RB up here into an array by adding your square brackets, or change get components back to get component. And again, we just want to use one. That was a typo a second ago. So right after this line, now that we've captured a reference to this rigid body right here, we can start customizing these settings. And for the ball, since it's going to be bouncing around the scene fairly quickly, we actually have a number of settings that we want to adjust ever so slightly. The first one is the fact that I don't want the ball to have gravity at all. So if you notice over here in the inspector, we have mass, drag, angular velocity, use gravity. So it stands to reason that if I type RB dot, somewhere in this listing, I probably have something related to gravity. So let's just try to type out gravity. Oh, right there at the bottom, use gravity. So I'm going to set use gravity equal to false. This will disable that checkbox over in the inspector when the program actually runs. The second piece of this, the second setting, is I want the ball to respond within the physics engine a little bit more frequently than just any other random game object that's just kind of sitting out there. And in order to do that, I need to turn the collision detection mode up to a much more frequently checked value. And so if we look over here in our inspector, you'll notice down here at the bottom we have collision detection. And if you hit this drop down, you'll notice we have discrete, which means it kind of sits around. It doesn't really check all that often. Continuous, it checks more frequently. Continuous dynamic, it's actually moving around a lot quicker. It's a fast mover. And then down here at the bottom, continuous speculative, that's a kind of trying to anticipate where it will be. What we want is continuous dynamic. But again, I'm not going to change the setting here in the inspector. I'm actually going to change it in code so you can get a sense of what's actually happening on the code side. So the rigid body dot has a collision detection mode, and we can set that equal to a specific value. Now the thing is, Unity has a bunch of these settings, a bunch of these values built in, and Visual Studio knows about those values, those containers of values. And so as we type out something, if Visual Studio can make the link, it can recommend certain values or certain containers of values. And in this case, you'll notice down here it says collision detection mode, and the tooltip over here is slightly different than anything we've seen so far. It starts out with the word enum. And enum is short for enumeration. It's a series of values with a label attached to them. So if I press enter and then do a dot, you'll notice I have 4 different values very similar to what we saw in the inspector just a second ago. And if I go down through each item, you'll notice the tooltip over here, collision detection mode dot continuous equals 1. If I go to the next one, equals 2. Go to the next one, equals 3, and the next one equals 0. Now, I, as a human, don't care about the value 0, 3, 2, and 1. What I care about is the fact that I have a word that makes a little bit more sense to me. Behind the scenes, the engine understands what these numbers are, understands how they operate, but in this case, I just want to pick continuous dynamic, hit enter, and use my semicolon. Now again, if you want more information on what's actually happening here, you can put your cursor on either continuous dynamic or collision detection mode and press F12 or right click and go to definition, right there. And that will take you to where in the engine the values and the labels, these discrete values over here, we have a label on the left and a value on the right, all bundled up inside this collision detection mode. So again, enum is just an enumeration. We're enumerating values. This listing just happens to have a logical sequence of 0, 1, 2, 3. Others out there, other enums might have completely different values, which we're actually going to see here in just a second. But realize that it's just a sequence of numbers, and we can make use of them using these labels. So it's a little bit easier for us humans to read and understand what's actually happening. Because I have no idea what equals 5 would be. But if it's got some special name associated with it, then that probably makes a little bit more sense. So the next item is, if you take a look over here in the inspector, we have down here at the bottom constraints. Now, these constraints represent the ability to basically freeze the different ways that this particular object can interact in the scene. Can it go left, right? Can it go up, down? Can it go in and out of the scene along the z-axis? Can it rotate along any of its 3 axes, x, y, and z? So notice freeze position, freeze rotation, and we have checkboxes. Now you might be asking yourself, well, okay, so are these just like a sequence of 6 booleans? Or how exactly is something like this written out? Well, it turns out that enum we looked at just a second ago for discrete, enums can also be used in what is referred to as flags. They're specialized individual values that can turn on and off at the bit level what's inside something like an integer, right? An integer is just a number, but internally, as the computer sees it, these are just a bunch of just a bunch of bits turned on or off. And so in flag mode, these things can actually represent, because remember, a Boolean is just true or false, on or off. So we can turn on and off these individual items, or the entire position row here, or the entire rotation row, or all 6 of them at the same time. And it turns out because these are enums, we actually have each of these labels listed for us. So if we jump back to the code and we start talking to RB dot, and we said over in the inspector it was called constraints, right there, RB dot constraints. And in order to assign this, we set it equal to something. And in this case, because I'm going to run out of real estate on this screen, I'm going to drop down one line. And in order to talk to the rigid body's constraints, if we start typing rigid body, notice the autocomplete says, I think you're talking to a rigid body constraints. Is that correct? Yes, it is. So if we do rigid body constraints, also notice the color is slightly different. It's kind of this green olive drab kind of color. So it's representing a value behind the scenes. And so off of this rigid body constraints, if we do dot, notice we now get a whole bunch of values, not just 4, but a bunch of them. And notice that the tooltip popping out to the side for freeze all, that's all 6 items, it says that its value internally is 126. Now again, as a human, I have no idea what 126 is, but I do know that freeze all will check all 6 of those boxes. And if you take a look at the next item down, that's apparently 14. The next item is 2, and so on. So in order to properly use this, what I want to do is freeze the ball's ability to go into or out of the scene along the z-axis. So I need to freeze its position in the z. So off this dot, we have freeze, and you might be able to kind of get, kind of narrow down F pause. So it's kind of, narrowing the search, or rather the list of available options. So in this case, F pause gets me close, and I said I want to use freeze position Z. So freeze position Z. Now in order to combine different values, in this particular case, I also would prefer the ball not rotate in any way. Now, in order to attach additional values, kind of like what a plus would do, here, since we're adding flags together, we actually have to use one vertical bar. Remember from the if statements and logical comparisons and that kind of stuff, logical and logical or conditional and conditional or from a few lectures ago, a double vertical bar means a comparison. Either the value on the left is true or the value on the right is true. It's a logical or. But in this case, since we're using what's referred to as the bitwise or, this acts kind of like addition. So we only need one. So it's very important to remember, comparison uses 2. In this case, adding them together uses 1. So after that one vertical bar, we're going to drop down a line, and we want to add one more constraint. We want to constrain the rotation. All 3 XYZ axes. So that's going to be rigid body constraints dot freeze rotation. I need to capital R. There we go. FROT. And we have, again, it kind of filters down to our results. We're not going to use any of the 3 individual axes. We're going to use the entire rotation. So right there at the very top, freeze rotation and semicolon. So now that I've got the ball configured so it stays fixed to my Z plane, right? Or rather my XY plane, flattened up against this scene. It can't go into or out of the scene, and it can't rotate. Now we need the ability to actually launch the ball into the scene. Now, if we come down here after update, drop down a couple of lines, launch is actually, in the very near future, going to be called by the paddle. The paddle is going to be responsible for listening to us moving left and right, lining up our shot, and then also pressing the space bar. But for now, we're going to write some playtest code right here inside the ball. So the first piece is this method that will launch the ball needs to be public so that the paddle can eventually make use of it. So public, and then it's not going to return anything, so void. And the method's name is launch. it doesn't take anything into its parentheses. No parameters, no arguments, none of that stuff. And then inside the body, what we want to do is basically establish the ball can go vertical, but then we want to say to the left and to the right, we have this kind of launch cone. And it's going to be 90 degrees, 45 to the left and 45 to the right, that the ball is able to be randomly picked. You'll randomly pick a direction, and whatever is randomly picked, that's the direction the ball is going to be fired. So in this case, what we want to do is establish a minimum degrees and a maximum degrees. Minimums to the left, maximums to the right. So we need a float min degs, as in minimum degrees, and we want to set that equal to 45.0f. And because we want one more float, we can just use a comma and declare the next variable, max degs, maximum degrees, and assign it the value of 135.0f rather, and then semicolon. So this gives us, from the center line, 45 degrees to the left, and from the center line, 45 degrees to the right. So 135. So 45 to the left, 0 through the center, and 45 more degrees is 135. Now, what I want to do is take these two ranges and randomly calculate a value between them. Just randomly pick a number between those two endpoints. I want to do this a certain number of times just to verify that my code actually works. Because this kind of code, the random, the range checking, that kind of stuff, can potentially be, it can be error prone. So what I want to do is create myself a for loop to run 50 times. 50 is a good sweet spot, good middle ground to see the code and confirm that it does work. So for, we want to start out at 0, so int I equals 0, semicolon. That's the initialization part of the for loop. The conditional, the middle piece, is going to ask while I is less than some number. And we said we want to go 50 times, so that's 0 to 49 iterations, semicolon. And we need to update I, so I plus plus. That's that final update phase of the for loop. And give your for loop a body. Now, inside the for loop, we want to randomly pick between minimum and maximum degrees, and then convert that into an actual degree. Sorry, from a degree to a radian, and then from a radian into our direction. So we're basically going from something that's a little more understandable by humans, right, degrees, to something that's more understandable by the computer, radians. So the first thing we need to do is figure out a new float, and this will be our degs, our degrees. We're going to assign that to a random dot range. And what are we looking for? We're going to feed in the values min degs. And notice the tooltip here, float min, float max, min degs, and max degs. So now that minimum degrees, maximum degrees, somewhere between this range has been randomly picked, we hold on to that value inside our degs, our degrees. Now we need to convert that into radian so that the computer can work with this stuff more in terms of trigonometry. So we need another float that's going to be our rads, our radians. And in order to calculate radians from degrees, you need to take your degrees value and multiply it by the constant that represents conversion between those two coordinate systems. So in this case, the MathF library actually has that value built right into it. So if you type in mathf dot, right here, deg to rad, that's degrees to radians. If you take a degree and you multiply it by this number, you'll get back a radian. Now, off the top of my head, I don't remember what the equation is. It's something like 180 divided by pi, or pi divided by 180 multiplied by your number. Essentially, it's the trigonometric function to convert from one item to another. Degrees to radians, radians to degrees. And there are a bunch of other items in here. This math library has a ton of different options to allow you to convert and do a bunch of different things. Right there is rad to degs. So in this case, what we want to use is our degrees to radians, right? Degrees over to radians. And now that we've calculated a radian value, what we need to do is extract out the x component and the y component. So in order to do that, remember what we're doing is we're plucking out the x and y in order to rebuild, up here at the top, the direction vector. This is the new launch vector. So in order to sort all that out, we need to fill in the dir vector, the direction vector, with a new vector 3. And what values are we going to feed in? Well, it turns out if you type in the parentheses to trigger the constructor for the vector 3, you'll notice there are 3 available to you. The first version doesn't take anything in. It internally defaults everything to 0. The next version down takes in just an x and just a y, and then the next version takes in all 3, x, y, and z. We actually want to use that middle one, x and y. Z is going to be 0 by default. And so in order to figure out what x is, it turns out that if you get the cosine of a radian, that's the x value. And once again, the MathF library has cosine right there as cos. And since it's a method, it's going to accept a float. So here we want to feed in rads, our radian that we calculated earlier. Now, that's the x. And in order to calculate the y, we do our comma. And the y can be extracted by using the sine method. So mathf, once again, dot sine. And inside the parentheses, we need to feed in some kind of float. And, well, we're talking to rads again, so just feed in rads. Close off sine, close off the constructor for the vector 3, and semicolon. Now, this is fine, runs 50 times, potentially works, but I might have accidentally done a typo in here, right? I might have accidentally, instead of using degs right here, maybe I used one of my min or max degrees, something like that, something to generate an error. So if I saw this code visually shown to me on the screen, if I saw it like 50 times, I'd know that there was something wrong because I'd see the same printout or the same visualization every single time. So what I want to do is take dir and visualize it. Well, it turns out that the debug class isn't just for logging. It actually has the ability to draw different items. It can draw lines and it can draw rays. And since dir is actually a ray from a center point up and to a specific vertical and horizontal, which is the x and y, then we can render that, whatever that line is, whatever that ray is more specifically, from wherever this particular object, this ball, happens to be sitting. So on the next line, we need to call out to debug.drawRay, and in these parentheses, notice there are 4 different versions, 4 different overloads, and we can actually look through those items if you want to. But notice that we take a starting location, a direction, a color, and a duration. We can ignore this depth test if we go back up 1. There we go. So where are we? Well, I need to talk to this game object's transform. And in order to get the transform, I can explicitly call out that I'm talking to this class. I don't need it, but I'm going to write it anyway. And in the next few lines, I'm going to use a very similar method. And there, I'm going to purposely omit this so you can see that we don't actually need it. But off of the this, which represents this class, I can talk to transform, lowercase t, transform. And from that transform, I can get my position. So that's where we're starting. Well, what direction are we going? Well, we just calculated the direction. It's dir. The next argument is the color. So this item, I actually want it to be yellow. So I'm going to use color dot, and these colors through here, these are all shortcuts to existing kind of values behind the scenes. Now you can obviously come through here and manually create your own values, and the color constructor, if you made a new color, would take in an RGB, and I believe there's another one for alpha that you could feed in values manually. But for the moment, these shortcuts will suffice for what we're trying to do. So color dot yellow. And the final argument is duration. Normally, a draw ray or draw line method will only render for one single frame. But in this case, since I'm only going to launch once, I want to see it stuck around. I want to see the line stick around on my screen for just a few seconds. So I'm going to plug in 15. This is the number of seconds that this line is going to stick around. Close off the method with our parenthesis and semicolon. Now it turns out, as we have just calculated our direction, this is going to be, the idea here is a direction is usually a unit length, right? It exists on a unit circle, and then we multiply that by some value in order to get a magnitude. Well, the magnitude for this particular item is going to be how fast it should go. And the combination of direction plus that magnitude, that distance, is going to be plugged into the velocity to make the ball fly around the scene quick. So that value is actually right here inside speed. So speed is going to represent our magnitude in a given direction, and direction is going to be unit length. So in order to calculate that, we have a couple of different spots where that pops up. One, right here when we're launching the ball, and two, when we bounce around the scene and we bounce off of surfaces. We need to recalculate the direction and then turn around and apply the new, or the original speed to the new direction. Well, since I'm writing or would be writing the same concept a couple of times, this is a violation of the dry principle. I don't want to write it multiple times, so I'm going to wrap it up in a method and call that method in the locations that I need. So just after launch, if I put my cursor just to the left, it's going to glow blue on the matching curly bracket. So down here at the end, but I'm still inside the class. Note, I'm still indented by 1, just before this closing curly that the tooltip tells me is the class. This guy right here is launch. So right after launch, I'm going to write a method. It's not going to return anything. It's going to be called apply velocity. And it's not going to take anything in, so nothing in the parentheses. And inside the curly brackets, inside the body, what we want to do is calculate the new velocity for this particular object. So because I'm also changing what the velocity is, I should hold on to that in that variable we talked about, velocity last frame. So here inside apply velocity, we can do velocity last frame and assign that to whatever the new calculation is that we're about to calculate. But I said I want to change the rigid body velocity to that value as well. So I'm going to do RB, talking to our rigid body, and our velocity off of the rigid body. And I want to assign that to a value as well. And what's that value going to be? Well, that is the direction. And again, I want to reinforce the fact that this is unit length. So I want to do dot normalized right? This will flatten it to a unit circle. If it's too short or if it's too long, it will bring that length back to a 1 length all the way around, a magnitude of 1. Which means when we multiply it by speed, speed will be the only factor that elongates or shortens the direction vector. So what this code is doing is over here on the right-hand side, it's calculating some new vector, and it's assigning that value into rb.velocity. Then rb.velocity gets read, and its value gets fed into the velocity last frame. So it's just calculate something, set it, and then read it in order to set it. So we're setting multiple items kind of all in sequence. And if I've just calculated a new direction, I would also like to visualize this, just in case. It also helps kind of iron out bugs should they pop up. So right after this line, let's do another one of our debug.drawArray, draw array. And where are we going to start? Well, in this case, also notice that this is kind of shaded out. If you mouse over it, says this can be simplified. It means it can be removed. It doesn't necessarily need to be there. So in this example, I'm going to omit this dot and just talk to transform directly. Transform dot position. The next item is what our direction is. Well, we already calculated dir.normalize times speed, and we held on to it in both rigid body velocity and velocity last frame. So we just need to recall one of those two items. I'm going to use rb.velocity, and then our next argument is going to be what color do we want to render this with. So I'm going to pick color.blue. And how long do I want it to stick around? Well, that's also going to be 15 seconds. So close that method off and semicolon. And now that I've got the ability to both see it when it first calculates its new direction 50 times, and then when it bounces off something or when it first fires, we can see its new direction multiplied by speed. We can see that as blue. Now I need to actually apply velocity. I need to call this method somewhere. Well, the for loop just runs and generates a new direction. There's no reason to apply the velocity 50 times. So after the for loop, but still inside launch, I'm going to call apply velocity. Okay. So now the idea here is as the ball gets fired into the scene, it can bounce off of surfaces. So in order to bounce off of surfaces and get a new reflection, we're going to come down here after apply velocity, drop down a couple of lines. I'm going to make another method, but the thing is, this method already exists inside Unity. Unity already knows about it, and it provides that information to Visual Studio. So the method in question is on, and notice I have a bunch of other ons right here. And so if I do collision, I actually have several different types of on collision. We've got enter 2D, exit 2D, stay 2D. We're not dealing with the 2D stuff, but we have when it first collides with something, that's enter. When it leaves, that's exit. And if it stays resting against the object, that's stay. So in this case, I want on collision enter. Now when I bring this code in, if I hit enter or double click or tab, what you're going to see is this code snippet that's written over in Unity, it provides me void on collision enter, and it knows about what it collided with. But we also, because of the code snippet, we also get private right here at the beginning. Now it's important to realize that all of our methods, right, apply velocity and any other methods out there have private in front of them unless we explicitly say otherwise. So launch, we're overriding private by saying public, meaning it can be seen by the outside world. Our variables, our fields up here at the top, they also have private in front of them. It's just because it's the default of the language, we don't actually write them explicitly. But if you needed to make these things public, you would put the keyword public right in front of them. I actually want to see speed in the inspector, so I have the option of either making it public float speed or using serialized field right above it. Serialized field lets me still see it in the inspector, but keep it secret so no other file can see it. So basically just protects the data. Now here inside on collision enter, we want to do a couple of things. Well, actually 3 things. The first thing is if for whatever reason we start playing and the ball, I don't know, for example, the ball is sitting so close to the paddle that maybe it triggers this on collision enter call. It's totally possible. When objects are really close, they can make that happen. So instead of responding to that collision, just because we're starting up and they're so close to each other, what I want to do is have the game manager track a variable that says whether or not we've actually started playing that level. So this does not mean the editor in terms of its play button. This means we load into a new level and I'm waiting to press the space bar. When I press the space bar and the ball starts bouncing around, that is playing. That's the context that I'm talking about here. So what I want to do is somehow listen for the fact that we're playing or we're not in order to actually do the rest of this code. Well, it turns out that in order to do that, I need to go back over to the game manager, and up here at the top where we have our properties, I need to make one more property. So right after our properties comment, but before our public static game manager instance, I need to make a public property. It's going to be a bool, and I'm going to call it is playing. And this property needs the body, so we have our curly brackets. We need a getter, semicolon, and a setter, semicolon. And the idea is as we move from level to level, we'll reset this so that we can line up our shot again, right? Because if we go from, let's say, level 1 to level 2, we don't want the ball to immediately start bouncing around in level 2. We'd rather have it reset so we can line up our shot and then press the space bar and have a little bit of control over the game. So now that we've got is playing, this public bool is playing get set property, if we jump back over to our ball.cs, what I want to do is inside on collision enter, I want to ask if we are not playing, just go ahead and leave. We've not actually started playing the game. There's no reason to process the code. So remember, the not is the exclamation point. So we can ask it the question, if we are not, and where does that data, that property we just created live? Well, it lives inside the game manager, and since the game manager is a singleton, I need to talk to that instance property. So in order to do that, for those static variables, we talk directly to the type. So game underscore manager dot instance dot, and now we can talk to the item in question, the is playing. So what this says is if we are not playing, then we don't want to do any of this of the following code. We actually want to, here inside this if's body, what we want to do is just warn, or we're kind of giving information to you, the developer, that, hey, we saw this method, this on collision enter, it happened, but we're not actually playing yet. So in order to handle that, we're going to do a quick debug.log warning. And inside log warning, again, this is mainly informational, but I want to elevate its severity just the tiniest bit. So if we see this, it draws our attention to it. And the message that we want to send is the following string. The first piece is, what class are we in? What's this type? And that is the ball space. What method are we in? In this case, since it's on collision enter, I'm going to abbreviate it to be OCE. So OCE. And what was the issue? Well, this method was called, but we're not playing. So, but not playing. And then close off the string, close off the method, and close off the statement with your semicolon. So if we start playing and we've not yet pressed the spacebar and this method gets called, which it has a tendency to do because the ball is so close to the paddle, we'll get this code. It'll say, yeah, we're not yet playing. You've not pressed the spacebar. So it'll print this ball OCE, but not playing to the console. It's just a reminder that, yeah, there's other code that does get run behind the scenes. So if this is the case, all we want to do is return. We don't want to actually process anything after this next line. But if we are playing, if we have pressed the spacebar, then we want to let the code after that if do its thing. So what's it going to do? Well, the second piece of this whole method is we're going to calculate a new direction based on the surface that we just bounced off of. So we're going to fill in dir with a new value, and that value is going to be equal to whatever vector3 dot reflect returns to us. And vector3 dot reflect takes in a couple of things. The in direction is the direction that we were colliding with an object, and the in normal is the surface normal, the line perpendicular to the surface that we actually collided with. So that's a ray coming straight out of the polygon we just impacted. So the in direction, it turns out collision has a lot of physics-related information, but this is after the fact. This is after we've processed the impact, which means the information coming out of collision has actually lost a lot of its impact, right? It's been kind of it's slammed into a surface, and you lost that momentum, that value. So here, the indirection is what we previously held on to. And what did we previously hold on to? Well, that's velocity last frame. So we can plug in velocity last frame. And who did we collide with? Well, that part is still okay. So, comma, and we can ask collision for the contacts. These are the things that we just ran into. And contacts is an array, so we need, you can mouse over it and see right there, contacts is a contact point array. So we actually want the very first item we collided with. So square brackets 0. And if we just collided with something, we have information about that thing, the point that we just hit, what it was, the other collider, and so on and so forth. But mainly we have the normal, the surface normal of the thing we just collided with. So plug that in, close the method, and in this case I actually didn't need a second parenthesis. It looks like there was already one there, so semicolon. Okay, so just double check that you're using the one parenthesis to close off that line. And now that we've recalculated dir, remember, if we scroll up a couple of lines, we just recalculated dir up here inside launch. Then we need to call apply velocity to actually apply the speed multiplier. So down here inside on collision enter, right after we've calculated a new direction, drop down one line and say apply velocity. Parentheses, because it's a method, semicolon. And hit enter a couple of times. Now, the third piece of this puzzle, of this method, is, well, if the ball is bouncing around the scene, it's going to be bouncing off the walls, the ceiling. It won't bounce off the floor. We're actually going to slice right through the floor. It can bounce off the paddle, but it can also bounce off of a brick. And if it bounces off of a brick, then we would want to do some kind of scoring information. Maybe we hit the brick enough times that we can destroy it. But all that information is going to be unique per brick. one brick right next to another brick might have completely different scoring information, might have completely different hit points or hit counts that we have to hit it. And so you strike the first brick and it has 1 hit, but the brick next to it still has 0 hits. And then you hit that other brick and it has 1 hit. So internally, it's tracking its unique points values and its unique hits values, as well as how many times it's been hit. So in order to talk to a brick, what we need to do is kind of have ourselves a little placeholder brick. So brick B, semicolon. And we want to try to fill in B. If the thing we just hit does have a brick component on it, then we know that we've hit a brick. If it doesn't have a brick component, then we hit something else, a wall, a ceiling, a paddle, any other objects you try to jam into your scene. So in order to do that test, right, we want to tell the brick that it needs to process some information. So we need to talk to brick, to this B variable. But it's possible that we could get back null. So if we get back null from the object we're colliding with, we don't want to talk to the brick. So we need to do an if check to see, do we have a brick or do we have null? And in order to do that, we can actually combine those operations. So we can fill in B with the thing we just hit. We can ask it if it has a brick component. So the thing we just hit actually comes to us from the collision object. So collision dot, and we can actually get the game object that we just collided with. So lowercase g, game object. And off of that game object, we can ask it to try to get component. And what are we looking for? Well, inside the diamond, we're looking for a brick. And again, get component is a method, so we need our parentheses. But it turns out, when this line runs, B is going to be filled in with a brick if we hit a brick, or it's going to be null if we didn't find a brick. So we need to do an if check on this B variable. Well, sure, you could try to throw in a semicolon and on the next line ask if B does not equal null, but we can ask it directly because this line resolves to being whether or not B has a brick or B has null. So we can just question B directly. So if parenthesis on the left-hand side of B, and over here on the right-hand side, we just add a closing parenthesis and give that a body on the next line. So all this equals collision, game object, get component, brick, all of that goes off and finds or doesn't find a brick, and it fills in B. So then we just say, if B has something, process it. If B is null, don't process it. So the simplified resolution of all of this expression becomes B, and we just test B. So now here inside the body, what we want to do is talk to the brick class. Now this is a scenario where we want to talk to it, but there's not there's no current content in the brick. There's not functionality to drive what we want to try to do. So what we want to do is throw in one of our to-dos, right? / to-do, colon. And here I want to say, fix this later. Now, when this code gets written inside the brick, and towards the end of this project, when we come back through and we do our cleanup pass on all these to-dos, when we clean up this code, because the bricks code will then exist, this code will then function correctly. So on the very next line, still inside the ifs curly bracket body, we want to say B dot, because we're going to talk to the functionality that's inside the brick class, which doesn't yet exist. This is fine. And we want to talk to a method that doesn't yet exist called hit taken, parentheses, semicolon. Now, since it doesn't exist, I don't want this system to continue generating this error, right? It doesn't exist in this context. So what I want to do is go all the way to the left and just comment this whole rest of this line out. Later on, when we come back, we'll clean up the to-do, and we'll also uncomment the b.hitTaken. And since it will exist, this line will no longer give us an error. Okay? So now, this handles colliding with objects, specifically colliding with walls, floors, the paddle, or bricks. And if we happen to be a brick, we interact with it. But if the ball hits the floor, then the idea is I don't want to collide with it in the traditional sense. I want the ball to basically slice straight through the floor, and the floor act as kind of more of an ephemeral or a ethereal object, right? It's more of a ghost. It doesn't actually exist, but it still triggers some code. I want it to be a trigger. A trigger is a collider that doesn't actually respond with collision. So after our closing curly for the on collision enter, I'm going to write another method, and once again, this is part of Unity, so Visual Studio knows about it, and it's going to be called on trigger enter. And if you notice, we have on trigger enter 2D, exit 2D, stay, and stay 2D. Basically the same things that we saw for the on collision variants. So we have two different support systems in play. So I want to use on trigger enter, and Unity will give me the code snippet inside Unity through Visual Studio will give me the private keyword here at the beginning. You could get rid of that. I'm going to leave it just so it's there, so it makes it a little more clear what's actually happening. But you'll also notice that on collision enter gave me a collision object, right, this type, and then the variable name, this parameter name, was called collision. But on trigger enter has a collider, different than a collision. And they changed its name to be other instead of collision. So we're now dealing with a different kind of object. Internally, they probably handle the same thing in similar ways, the collision versus trigger, in similar ways, but they can optimize for different aspects by putting it in different spots like this. So make the game just a little bit faster, make the engine just a little bit faster, potentially. So now that we're dealing with on trigger enter, what we want to do is something very similar to our if we're not playing, just warn about it and leave. So we can do if not game underscore manager dot instance dot is playing. So if we are not playing, let's go ahead and warn about it. So debug dot log warning. And the string we're going to send is ball because that's the class we're in. The method is changed. We're no longer in on collision enter. We're in on trigger enter. So OTE. And the same piece right after that. So hyphen and but not playing. We encountered on trigger enter coming off the ball, but we're not playing. So close the string, close the method, and add your semicolon. And if this is the case, we want to leave immediately. So on the next line, return semicolon. But if we are playing, is playing will be true. This not will make it false, and if false means none of this code actually runs. So then we jump on to the next line, and what we want to do is if the ball has hit a trigger named floor, then we know that we've potentially lost. So right after our if, after it's closing curly, we want to say if, well, who do we run into? Well, that's the other right here. So if other dot, and in here a collider is treated slightly different than a collision. So here all we need to do is ask for the name. So if the other's name is equal to floor with a capital F, then we know we've hit the item that causes us to lose. And so inside the curly brackets of this if, number one, we want to call lose, but it doesn't yet exist. It will shortly over in the game manager, but since it doesn't currently, we want to do a to-do, fix this later to remind ourselves. And the method is going to be off of the game_manager.instance, and it's going to be called lose. Okay, so game_manager.instance.lose parentheses semicolon. But since this doesn't exist and this is going to give us errors and I don't want to deal with those errors, we're going to go over here to the left and just comment that line out and come back to it later. So this is actually a good place to save. So both of these two files have changes. So I'm going to hit Save All or Control-Shift-A. And now what I want to do is we're bouncing around, colliding with stuff. We're calculating, or rather, we're using the velocity last frame to calculate a new direction, but we're not actually holding on to the velocity last frame. We're not remembering it. So up here inside update, what we want to do is repurpose update to follow in the footsteps of the physics system. So the physics engine. So number one, update is called every frame when the engine gets around to it. Towards the beginning, towards the middle, towards the end. It's called at some point in that sequence. But fixed update, the physics engine's update, can potentially be called multiple times per frame or delayed frames at a time. So we don't necessarily know when it will be called. We just know that it will be called at some point. So this comment up here about being called once per frame is irrelevant. We're actually no longer talking to update either. So I'm going to triple click this line 26, and just get rid of that comment. And I'm going to repurpose update to be fixed update. And if you write that correctly, your color should also change to this blue, assuming you're using a similar theme similar theme to the one that I'm using. And so here inside fixed update, what we want to do is basically say, if we're running, then let's go ahead and start processing some things. But if we're not running, then we can just leave. Very similar to what we dealt with down here in on collision and on trigger enters. If we're not playing, just leave. So in this case, we're not actually going to warn about it because that would saturate the console with a bunch of logs. We're just going to leave. So here inside fixed update, let's go ahead and say if we are not game manager.instance.is playing, if we are not playing, let's go ahead and just return. But if we are playing, we need to do a couple of things. One, we need to make sure that we're actually using a correct velocity. Now, if we drop the X or Y values to 0 and we need to nudge the ball, that needs to happen. So before we try to capture the velocity last frame, we need to hold on to, or rather, we need to check for those edge case bugs and fix them accordingly. So in order to do that, I'm going to come down to just after apply velocity, but before on collision enter. And between these two methods, I'm going to write another method. It's not going to be seen by the outside world, so private by default. Void, it's not going to return anything. And it's going to be called nudge if needed. So if we detect that we need to nudge the ball, then we'll do it. It doesn't take anything in the parentheses. But here inside the body, what we want to do is, first of all, if nothing has gone awry, right? Our velocity X and our velocity Y are perfectly fine, then we don't want to make any modifications. So we're going to start out with a pair of floats. The first one is called X nudge, and we can default that to 0.0f, comma, y nudge, and set that equal to 0.0f as well, and then our semicolon. So if nothing has happened, then those two values can be used to modify velocity. Adding 0 to something isn't going to change it at all. So I've dropped down a couple of lines, and I want to tell the rigid body velocity to add to itself, add to its existing value. So I need to use plus equals. And what are we going to add? Well, that's going to be a new vector 3, and the information that we're going to feed into it, how much to nudge in the x, how much to nudge in the y, that's going to be filled in with our x nudge, comma, y nudge. So now we need to actually fill those two out. So between our floats and our rigid body modification, we need to examine each axis, the x first followed by the y. So I need to check if, and I want to see if the rigid body.velocity.x has dropped below my nudge factor threshold. Now it can be negative, it can be positive. I don't care, I just need to know if it dropped below my positive threshold on either side. So in order to do that, I need to get the absolute value of that velocity.x. So again, mathf to the rescue, mathf dot abs for absolute, and into absolute we're going to feed rb dot velocity dot x. So now regardless if it's negative or positive, we get back whether or not it's close enough to 0 that it's below our nudge factor. And then we just want to ask, are you below, so are you less than, nudge factor? And if you are, then we want to compensate for the issue. So here inside the body, we want to recalculate a good nudge to be applied to the velocity. Give it a little push back into our level. So what we want to do is fill in x nudge with some value. Well, remember earlier, just a few lines above this, we used random.range, and it had floats. Min-degs and max-degs are floats. Well, if you mouse over and you take a look at what's going on here, Visual Studio 2019 seems to be hiding it at the moment, so I'm actually going to jump back out to my browser and go over to Google, and we're going to look for Unity Random Range. So if I go to this scripting API for random.range, what you'll notice is we've got two different versions. This guy up here takes a pair of floats, and this guy down here takes a pair of integers. And if you read the comments, the float version says that it's inclusive. So if you go looking through, let's see here, min is inclusive, max is inclusive. Meaning if you feed in one number on the left and one number on the right, you'll get between those two numbers and also potentially including those two numbers. So 0.0 up to 1.0, you'll get all of that range. If you use the integer version, the minimum is inclusive, meaning you'll get your 0 right here, but the max is exclusive right there, meaning it internally will subtract 1 from the number. So if you fed in 10, you're only able to go up to 9 because internally it subtracts 1. Now this is mainly because when you tend to use the integer version, you will probably be using it with something like an array. And arrays have to count 0 based. So you can't go just increasing to the total number. You have to subtract 1 from the maximum. So Unity basically gave it to us for free. They take 1 off the top so we don't have to remember. This is actually one of the more common issues that early developers that are working with arrays run into. You accidentally forget that you need to subtract 1 from the maximum value, and it causes an index out of range exception, which then crashes your program. So in this case, I'm going to use this concept, the max exclusive, to my advantage. So back over here in the code, if we go back down to nudge if needed, what I want to do is calculate a multiplier. So the nudge factor value here, I want to apply that either to the left or to the right randomly. I don't care which side it's on. This code gets called so frequently that, if we're constantly bouncing into a wall and it gets called a number of times, statistically or probabilistically, it will eventually call it for the other side, which then brings us to the left of the wall that it's slamming into. So I'm not really worried about repeat calls to this because it happens so quickly, it generally won't be noticed. So what ends up happening here is, since I want to randomly pick either left or right, I actually want to use the integer version to say, if I'm going to take this number and go either left or right with it, this is currently 0.01, I'd like negative 0.01 or positive 0.01. So I would need to multiply this by -1 or +1. And if I use the integer version of random range, I now get the ability to say, well, my minimum is -1 and my maximum is 1. So because it's an integer, that gives me -1, 0, or 1 that it could possibly pick from. But because of the exclusivity on the max that we just looked at in the documentation, I can't use 1 on the max. I have to add 1 in order to override or compensate for the subtraction that Unity does for me. So here I'm going to assign xnudge to something. What's that something going to be? That's going to be random.range, and the integer version can use -1 on its minimum, and because the max is exclusive, we need to add. So we would be intending to use 1, but remember we have to add 1 to it, so let's go with 2. So this will give us back either -1, 0, or 1. So then we can multiply this by our nudge factor, and that will give us either -0.01 or positive 0.01, which will then get fed into this xnudge, which then gets plugged in, added to the velocity. So when we come back around, rb.velocity.x would be either negative or positive 0.01, which absolute is going to flatten to always be the positive side. And since 0.1 is equal to nudge factor, not less than, we don't actually enter this code a second time. So xnudge remains 0. It remains unmodified or unchanged. So this handles everything for x. Now let's go ahead and handle y. The code is essentially identical. We just need to change which item we're looking at. So if mathf.absolute, ABS, we're looking at the rigid body dot velocity dot y. And we need to ask if that y is less than nudge factor. And if it is, we want to set y nudge equal to random.range, and again using -1 to 2 to get back -1, 0, or 1, and then multiply that by nudge factor, semicolon. So this will handle any scenarios where x gets so close to 0 that we need to nudge it, or y gets so close to 0 that we need to nudge it. And again, you can double check that you're using all your variables correctly by clicking once right here on xnudge. It shows up 3 times, and ynudge shows up 3 times. And then just make sure your if statement is checking x there and y there. Otherwise, you can still get into that 0 on the X or Y, and you get locked into those axes, and there's no way to actually win the game, and you have to stop playing and restart the level. So this allows us to correct for that anomaly should that issue ever happen. But we actually need to make use of nudge if needed, because right now we're not actually doing that. So if we scroll back up here to fixed update, what we want to do is after this if statement, let's go ahead and call nudge if needed. And now that potentially modified the velocity, and that's fine. Now we just need to remember the velocity. So a couple more lines down, velocity, last frame, let's set that equal to the rigid body velocity as it currently exists, modified by nudge if needed, possibly. And so this should allow us to keep track of all the information in order to play the game, bounce around using on collision enter, and so on and so forth. Now the thing is, if you save this code and jump back over to Unity and try to play, you're not really going to get anything. The game's not really going to play because there's no code telling it to actually launch the ball. So as a quick debug, as a quick test, just to verify that our systems are actually working, I'm going to come up here to Start. After our last rigid body constraint, and this code should not be enabled after we verified it, right? We'll just go through the process, make sure everything's working correctly, then we'll turn it off. So we want to do a to-do, and just like we did with the Game Manager's update, we want to say disable once verified. And the code is going to call launch, the method that actually launches our ball. And remember, we're using is playing in several spots. Right here inside fixed update to actually do the velocity calculations. We're also doing it in on collision enter when we bounce off surfaces. So we need to actually start playing. Well, how do we start playing? Well, remember, this is a property. It has a getter and a setter. Right now, we're just getting its value. We're reading it. But we need to write it. We need to set it. So right after launch, you can call game_manager.instance.isPlaying and set that equal to true. And save that file. Make sure both files are saved. Otherwise, you might get an error over in Unity if it doesn't know about the isPlaying property that we created. So now that those two files are saved, and assuming I didn't make any mistakes in this, and if I did, we'll debug it and figure out what's going on. If we go back to Unity, let that compile, we can actually playtest our code directly from level 1 right here, since we have a game manager. We don't need to go back to start. And let's just press play and see what happens. The ball should immediately fire itself out into the scene. And I'm going to pause for just a second. And notice over here in the scene view, or if you enable the gizmos over here, you can see it as well, but it's a little difficult with the blue. The yellow lines, there are 51 unit long lines coming out of right here at the center, because that's where the ball was sitting when we very first started. Now the blue lines are the same as the yellow, except they've been multiplied by speed. So these things are 10 units long, every single blue line, 10 units long, and the line itself represents the direction that the ball should be going. So you should be seeing, assuming that your code is exactly like mine and your settings, your setup is exactly like mine, you should be seeing the ball bouncing around the scene, and it is perfectly fine that the paddle has fallen to the ground. Remember, we haven't done any code, we haven't written any code, we haven't done any modifications to the rigid body. So it's still got gravity applied, which is what pulled it down to the bottom. But now if you just let this play, the ball is going to continue bouncing around the scene. You can see its trajectory, its path, over here with these blue lines. So if you stop playing and play again, you should notice that the launch direction should be random with every single run. So that one was up and to the right. This one is going to be slightly up and to the right. If you stop playing and play again, this one is up and to the right again. And the idea here is if I saw the same direction every single time up and to the left, I'd know there might be something going on with my code. But since I'm seeing a good 90-degree spread on this yellow sequence of lines, I know that that random over inside launch is actually doing its job. So there are 50 lines, and after 15 seconds, the lines start to go away. So we lost all the yellows, and now notice the blues are periodically turning themselves off. So at this point, I'm going to jump back to the code because we have verified it does work. Now, to do verify, disable once verified, we just verified. So let's go ahead and turn off launch and game manager. And so with those two lines of code disabled, if we save this, jump back to Unity, and let that finish compiling, when we play now, the ball, number one, it actually, because we haven't said that we're playing, nudge if needed isn't actually called because we're not playing, so we return. But if we were playing and our velocity hadn't gone anywhere because we hadn't launched, then nudge if needed would kick in and our ball would actually start to very slowly climb in a particular direction. So now that the ball is again back to stationary, now we can continue on with the next item, and that's going to be the paddle. So I'm going to stop this video. We're going to resume with the paddle in the next video. So if you would, please join me over there in the next video.